Okay, very good afternoon, everyone. Welcome to this week 4 uh, on this problem solving session. So, in the last week, you have studied second order systems, their time response analysis, and also gone through controllers. If you are attending this session, I would assume that you have gone through the lectures, you've gone through the lecture notes, you have also gone through the assignments and uh, also tried to attempt that. Then and only this session is going to be meaningful because I'm not going to teach here, though I'll be recapping uh, some of the important things, but mostly uh, we'll be solving questions. With that in mind, let's start today's session. So we'll start with second order systems. I'll just briefly revise second order systems. In the previous lecture, we learned what is type of a system and what is order of a system. When we talked about the type, we said we would consider OLTF, open loop transfer function, and see how many poles are at the origin. So we'll see poles at origin. That gives me the type of the system. But when we say order of a system, then we are considering closed loop transfer function. And in that closed loop transfer function, we are saying the degree of the denominator. We are saying the degree of the denominator. And that highest degree of the denominator, that is the order of the system. So basically, when we are studying second order systems, that means in our closed loop transfer function, the highest power of s in the denominator of that transfer function will be 2, right? So order will be 2 when it is second order system. So I'll just quickly write the OLTF, open loop transfer function of a second order system. I'm denoting it with GS. It's equal to omega n squared divided by S into S plus 2 zeta omega n. This is OLTF of a second order system. Why second? Like this is as of now OLTF, but when I write the closed loop transfer function CLTF, that will be C of S over R of S, right? And that is CLTF. We will get something like this: omega n squared divided by S squared plus 2 zeta omega n S plus omega n squared, right? So this form is called the standard form of a second order system, right? But here, what is important are these two variables, omega n, and second part is zeta. Omega n is called natural frequency or natural undamped frequency of the system. Okay, means I have a system, I give some input that oscillates with some frequency without any damping. If I do not employ any sort of damping in the system, the frequency with which the system will oscillate, that is called as natural frequency, and that is denoted by omega n. And this zeta, it is called damping ratio. This zeta is called damping ratio. Sometimes this zeta into omega n together, its multiplication, it's called damping factor. So you might be asked sometimes, what is damping factor? So in that case, zeta into omega n is damping factor. So basically, there are two important variables in the closed loop transfer function of a second order system, which is zeta, that is called the damping ratio, and omega n, which is the frequency, natural frequency, like, right? So now if we see this denominator of this second order system, it's something like this: s square plus 2 zeta omega ns plus omega n square. So if I put it equal to 0, this becomes characteristic equation of the second order system. And basically, this s is has the order 2. It means we will have two poles for this equation, two roots for this equation. It's a quadratic equation, so that I can write. For example, I'm denoting s1 and s2 to be the roots of this quadratic equation, and that will be using quadratic formula 2 zeta omega n plus minus b square, that is 2 zeta omega n square minus 4 into a into c divided by 2 into a. That's 2. Or if I take 2 common, what I will get? S1, S2, this will be equal to minus zeta omega n plus minus omega n into square minus 1. Okay. Sometimes this factor is denoted by omega d, right? So um, it's called as damping frequency, right? So this omega d, it's called damping frequency, right? So because omega n was natural frequency of oscillation. So if we employ damping, then we have different oscillations. We have different frequency of oscillation, and that's represented by omega d, right? Now, the response of our second order system, it depends on zeta, right? So by looking at the value of zeta, we can decide the response of our system. As I said, zeta is the damping ratio. It means if for example, if zeta is 0, so zeta is damping ratio. If zeta is 0, it means there is no damping. So the response will be something this. Let's assume there is some value. The response will oscillate because there is no damping. There is no damping, and the response will oscillate. This is the response CT, and this is with respect to time, because we are as of now saying time response analysis. We're doing time response analysis. So when there is no damping, the response will something be like this. It will be oscillatory, right? So if this zeta, if it is between 0 and 1, then my system is called underdamped system. You just remember this term. When my zeta is between 0 and 1, then the system is called underdamped system. So the response will be something like this. This is my time. This is my response CT. Let's assume this is the final value. So my response will be something like this. With time, the response will decay. Okay, so this is an underdamped system. For this underdamped system, the value of this zeta lies between 0 and 1. So if the value of zeta is equal to 1 exactly, then the system is called critically damped, right? So it's called critically damped system. And the response will be something like this. Why I am explaining this in detail? Because all of your assignment questions, they're based on this. So if you understand this, you'll be able to do every question. Let's assume this is my final value. So the response will be something like this. There is no damping because there is exactly. So what is this under damping means? So see, zeta equal to 0 means there is no damping. That's fine. But under damp means the system, there is damping, but less than what is required. That's why this it is not directly damping out the oscillations right from the beginning, because the damping is less than required. So I'll just write it here. Damping is less than required. That's why it's called underdamped system. In critically damped system, whatever the damping is exactly given, as much is the required. And in overdamped case, zeta is greater than 1. It's called overdamped. It means we give more damping than is actually required. So when we give more damping than is actually required, you will get system response something like this. If this is my final value, you'll get something like this. Let's settle down this because we give more damping. We give more damping. Okay. So this is the behavior of gamma. Now you can also see, you can also characterize these systems, like for example, overdamped, underdamped, or undamped. This system is called undamped when there is no damping. Undamped. So if you are given a second order system, you do not know the values of zeta. Still, you should be able to tell whether my system is undamped or overdamped or underdamped just by looking at the poles of the system. For example, since it's a second order system, so two poles will be there because it's a second order system. So if your poles are on the imaginary axis, if your poles are on the imaginary axis and they are different, like they are complex conjugates, but they are on imaginary axis, then your system response will be oscillatory. I told you in the second lecture, if you have repeated poles on the imaginary axis, then your system is unstable, means the response will go to infinity in that case. But that is not the case here. You have complex conjugate poles on imaginary axis, two poles. It means the response will be oscillatory and the system will be undamped. You don't need zeta. Then you can say for this system, zeta is 0. Right. Now, if your system has poles on the LHP, so of course, all the systems are stable or marginally stable, but it means there is no pole on the right half plane. So of course, the poles will be in the left half plane. But if they are complex conjugates of each other, if they are complex conjugates of each other and they are not on the imaginary axis, they lie in the left half plane and they are complex conjugates of each other. I'll just write complex conjugate. So that means the system is overdamped, right? So if they are on the if they are in the LHP and they are real and equal, if they are real and equal, then the system is critically damped. Real and equal. Then the system is critically damped. And if they are in the LHP, they are real but unequal. Real and unequal. The system will be overdamped. So this is just a gist I gave you. Based on the damping ratio, you can decide whether my system is overdamped, undamped, critically damped, or underdamped, right? But if you do not have the information of zeta, but you're being asked, but you are given this, you are given a second order system, so obviously you'll be able to find the poles of CLTF in that case. So with the help of those poles, you should be able to find whether your system is critically damped, undamped, or whatever, right? So now let's do one thing. This is one type of question. There are some 3 or 4 questions in your assignment where you are being asked, find whether your system is critically damped, undamped, or overdamped. So in that case, what you will do, you will just find the transfer function of the CLTF and then compare with this. We will do some questions. I'm just giving you a just as of now. Just compare with standard transfer function, and then from the standard transfer function, on comparing, find the value of omega n and also find the value of zeta. So when you have the value of zeta, you can decide whether whether your system is underdamped or overdamped, etc., and etc. The second type of questions that you have, they are based on find the performance specifications. For example, if you have an underdamped system, I'll just make the response of an underdamped system. Underdamped means there is less damping than is actually required. So I want my response to settle here, but I'm getting a response something like this. Let's assume my response is something like this. It means you should be able to identify, first of all, it's an underdamped system. For this underdamped system, there were some characteristics. Like, for example, you are given this response, how you will characterize whether my system is good or bad, whether for what application I'll use this system, right? See, this is the final value. This is, what should I write it here? Steady state. I want my system to settle here. This is my reference. I want my system to settle here, to settle on this value. But no, my system, what is my system doing? Is starting from here, here. It should stop here. It should stop here, but it's not stopping. It's going up and then going down, then again going down, then again going up, and then it's stopping somewhere here. It's taking some time. It's taking some time to stop at that position, right? So the initial moment, so when this system, when this system reaches 90% or 100%, this is 100% of course of this steady state value. So when my system reaches 100%, when this first touches this 100% in case of an underdamped system, that time, because this x-axis is time, that time is called rise time. That time is called rise time. But you will see one more definition. I should not teach this because we have already gone through the lectures. But you see, you might have also seen definition something like this. When my response reaches from 10% to 90%, this is one definition you will see, and the other definition you will see when my response reaches 0 to 100%. Again, both are rise time. Actually, this one corresponds to overdamped systems. This is for overdamped systems. Why is it so? Because overdamped systems are sluggish. If you see this system, they are sluggish. They will take a lot of time to reach this final value. You see, a lot of time is reached. So that's why, to compensate or more to make it resemble similar, this calculation, these values similar to those of underdamped systems, we take 10 to 90% for overdamped systems. Fine, leave that apart as of now. So what is rise time? Rise time is this time that system, when it first hits the steady state value, where it has to settle. But it doesn't settle there. It starts rising up and it reaches the peak value. This is the peak value. And the peak value, the time when it reaches this peak value is called peak time. And this peak value is called maximum overshoot. It's called maximum overshoot. Why I'm explaining this? Because we will be finding the values for this. Because then in your lectures, you might have studied them in detail, derived expressions for them. And now here, we will also be doing questions, because in your assignment, you have few questions where you are being asked find the rise time, peak time, settling time, overshoot, etc. and etc. So I just thought I'll just give you a brief overview what we are doing. So, and then when it has to come back, then again there are some undershoots coming. Finally, it settles down. Finally, it settles down here. So this time is called settling time, where the response settles to that value. But there is one thing. Some people will say, no, it's settling here because there is almost less error. Some people will say, no, it's settling here. Here, the error is more or less. So there are bands of settling time. Some people say, okay, if my settling time is within 2% error, band, then I'm okay with that. Some people say, okay, even if it is a 5%, a 5% band, I'm okay with that as well, right? So 5%, if there is 5% error, I'm okay with that time. So I can take that as settling time. Some people say, no, 5% is too much. I'll just only allow the values which are in 2% band, right? For example, if I want 100%, then if it is 98%, that's okay for me because that's in under 2% range. Fine. So this is my settling time. So now in your lectures, you must have learned the expressions for finding these parameters. So, okay, one important thing that I was talking about is, so when you have these values, rise time, peak time, settling time, overshoot, you should be able to characterize the system. For example, if I say I have a system where my rise time is 2 seconds, I have another system where my rise time is 10 seconds, right? It means the system with rise time of 10 seconds is sluggish, that is slow. But if my system with rise time of 2 seconds, that is comparative to the one which has 10 seconds, that's very fast. So sometimes if you want your system to be very quick, to respond very quick to your input, then that means you should have less rise time. Similarly, but if that is not the case, if that is not the case, if you want accuracy, if you do not want overshoot, you will go with, okay, there will be less rise time, but fine. Uh, Even if there is less time, rise time, but I don't want overshoot. You will go with this setting, overdamped setting. See, there is no overshoot. So it depends. We will see on the later part of this lecture that we use controllers. For example, you are being asked to find your system has a damping ratio of this, and which gives rise to a maximum overshoot of 25%. Let's assume do something, do something, and make this overshoot less, reduce this overshoot. So in that case, we will use controllers, right? Because then I will use controller to decrease overshoot or to improve settling time or to decrease rise time or whatever. There are different controllers that will come on the later part, right? So as of now, just remember these rise time, settling time, they are performance indices. By looking at these values, I should be able to characterize, okay, if my system has this much of rise time, then it should be something, it should behave something like this. That should give you an idea how a system is, right? That's why these parameters are very important when you study them, right? So now let's come to the questions. How we find these values of a system, like of an underdamped system? How do we find this rise time, settling time, etc., etc.? So in our question number one, we are given a system. So we will do good questions today. We are given a system omega n square s into s plus 2 zeta omega n. This is output C of s. Excuse me. Okay, so it's a unity feedback. See, it's a unity feedback system. This is your error, E of s. This is your input. This is your open loop transfer function. This is your open loop transfer function. Now, what is question saying? Question is saying, consider the system shown in figure where my zeta is 0.6, fine, and my omega n, the natural frequency, is 5 radians per second. Perfect. Now, what are we being asked? Find the rise time, dr, peak time, dp, maximum overshoot, mp, and settling time, ts, when the system is subjected to unit step. When the system is subjected to unit step, because when you have done the analysis, you have assumed your input to be unit step. I know you must have gone through the lectures where the professor has also solved a similar problem, and find the expressions for these parameters. Now see, this is my open loop transfer function and unity feedback. When I solve it, what will I get? CS over RS, it is what? Omega n square s square plus 2 zeta omega ns plus omega n square. This I will get because open loop transfer function is given. I'll just apply the negative feedback and get this. Now, you know what is the expression for this system. You have done the analysis exactly for this system with unit step input. You know, then what was the expression for rise time? That is given by pi minus theta over omega d, where this question we'll do in detail. Other questions you will do yourself. Where theta is what? Cos inverse of zeta. And I hope every one of you're having calculators with you. You're not getting any voice. Anybody has somebody has commented that no voice is coming. Is it still the problem? Please confirm. Shamita, is this the case with you? Are you getting my voice? Am I audible to you?
Audible, sir.
Okay, thank you. Thank you, Dhanraj, for confirming. So my theta is cos inverse of zeta, and my omega d, that is the damped frequency of oscillation, that is given by omega n into 1 minus zeta square. Okay, we know gamma, we know omega n, so we know omega d, we know theta, we should be able to find the answer. So now what is TR, rise time, pi minus, what is cos inverse of, okay, I'll write it as it is, cos inverse of 0.6. Please solve it and tell me the answer. We'll go step by step. Then omega d. Omega d will be, omega n is 5 into 1 minus 0.6 square. If you solve it, you'll get pi minus theta will be 0.93 radians. This cos of something theta, yeah. And omega d will be 4. And finally, you solve it, you will get 0.55 seconds. This will be your rise time. Fine. You have to remember this formula, otherwise you should know the derivation. Now, second thing is you have to find the peak time. Now, peak time. Peak time, TP, what's the formula for peak time? That is pi over omega d. Omega d we found out above, that's pi by 4. That will be equal to 0.785 seconds. This is your peak time. So similar, you have similar question in your assignment, so you have to do that in a similar way. Now see maximum overshoot, MP. Look here, this is very important, how you will calculate this. So the formula for MP is e raised to the power zeta omega n into pi by omega d. Right, so I'll just put in the values. E raised to the power minus, what is zeta? 0.6 into omega n is 5 into pi is 3.14 divided by omega d is 4. We calculated it. And when you solve it, you will get MP is equal to 0.095. And if we multiply it with 100, we get it as 9.5%. So the system should have stopped here. It should have stopped here, but no, because of overshoot, it will go 9.5% more. to then its final value, right? Then what did I say? Settling time. So then settling time. Now I said there are two criterias to find settling time. So I'll just write for 2% criteria. The formula is GS is equal to 4 by gamma into omega n. So 4 by 0.6 into 5, which is equal to 1.33 sec. Similarly, for 5% criteria, settling time is 3 by zeta into omega n. That's 3 over 3. That's 1 second. So this is what I told you in the beginning. If somebody says, okay, 5% is okay for me, then that will settle faster. This will be 5%. And 2% will take slightly more time. This will be 2%. That will come later on. This is also evident from the expressions as well. Anybody has any doubt in this question? Because you have similar question where you are being asked to find the rise time, settling time, peak time, and overshoot in your questions. This is one type of questions. These are one type of questions which you have, and they are very easy questions. That's why I will not focus more on the assignment today, but rather we will solve a good question that will also clear your concept, because the second order systems, they are very important, specifically for gate point of view. They're very important, right? So now let's solve another question. The open loop transfer function, keep your calculator with you. The open loop transfer function of a unity feedback. Again, I'll write for first few questions, I'll write full question. So you have given an open loop transfer function and with a unity feedback. What is the transfer function? Is given by 25 by s into s plus 5. So this is your OLTF. What you have to find? Calculate natural frequency of oscillation omega n, damped frequency of oscillation omega d, and also damping ratio zeta, and also damping factor zeta into omega n. I told you damping factor sometimes we call zeta into omega n. So we have to find omega n, omega d, zeta, and zeta into omega n. We have to find this. So what will be our approach? So we are given, see, this type of question is also in your assignment, but differently asked. See, you are given an OLTF, which is G of s 25 divided by s into s plus 5. But you know the standard form transfer function of a second order system, that is basically CLTF, right? So what will be my CLTF? CLTF, that is CS over RS. What will that be? That will be GS divided by 1 plus GS, because it's a negative unity feedback. So in the question, if there it is not mentioned, remember this from now onwards. If in the question it's written, it is a feedback, unity feedback, and it's not given whether it is positive or negative, then you will by default take it's negative feedback. Right? So it's negative feedback, because positive feedback do not give us good results. We have discussed that. So that's why we take negative feedback. So it's negative feedback. My CLTF will be this. And what is my GS? GS is 25 divided by S into S plus 5 divided by 1 plus 25 divided by S into S plus 5. When we solve it, what we will get? We will get 25 divided by S square plus 5S plus 25. This is my CLTF. This is my CLTF of a second order system, which was given. But you also know the CLTF, the standard CLTF of a second order system, that is given by standard. So you will do similar things. That is given by omega n square divided by s square plus 2 zeta omega n into s plus omega n square. Now we will just compare. So all the questions that you have in your assignment, you will be following the same approach. Find whether OLTF is given or CLTF is given. OLTF is given, make it CLTF. CLTF is given, then no need. Directly compare, right? So I think there in your case, direct CLTF is given, or just compare. So here, if you see, my omega n square is 25. What it means, my omega n square is 25. It implies my omega n is 5. Okay, 5, and the unit is radian per second. Done. Now I need to find zeta. What is, oh, see, what is my 2 zeta omega n? I'll just write here, compare. Compare these. My 2 zeta omega n, it is equal to 5. See here, it's equal to 5. I know my omega n is 5. So my 2 zeta into 5 is equal to 5. This and this goes. My zeta is 1 by 2, or it's 0.5. Now you see, you got omega n, you got zeta. What is omega d? Omega d is omega n into 1 minus zeta square. And what is zeta and n? Just multiply 5 into half, 2.5. Okay. So this will directly be 2.5, and this omega d, when you calculate it, you will get it 4.3 radians. I'm not going to solve it because it's straightforward. Why to waste time on this? Okay, so basically, when you have to solve such questions, just remember this expression, standard closed loop transfer function, and remembering it from now onwards till you are studying control. This will be everywhere. You'll be doing root locus, the CLTF will be there. You'll be doing polar plot, etc., etc. This will be there. And this sometimes is mixed up with many, many good topics. Perfect. So now let's do one more question. Let's do one more question. Yeah, it's a very good question. Very good question. The question is, the block diagram of a closed loop transfer system is shown in figure. So you have an R of S given. There is a unity feedback, negative unity feedback, and the forward loop transfer function is K into S plus 2. This is my output, C of S. There is another block in the feedback, right, which is 1 plus SP. So what is given? You are given this block diagram. It's shown, it's saying the block diagram of a closed loop control system is shown in figure. The values of, find the values of K and find the values of P. What is given? It's given that zeta is 0.7 and undamped natural frequency, that is omega n, is given as 5 radians per second. Okay, anybody? Anybody can give me an idea how we should solve it? You should be able to give me an idea at this stage because we have solved 2 questions. It's not that difficult. See, what is G of S here?
So first you need to find out closed loop transfer function.
Very good, very good. Then?
From that we need to identify natural damping.
Okay, good.
uh,
Then,
Natural damping is already given, sir, sorry.
mhm.
uh,
See, you said first step is correct. Let's do that one. Let's do that one. Darun Raj, let's do
uh,
that first step now, because when we do that, it will be very easier to visualize, right?
okay, sir.
So my G of S is K divided by S into S plus 2. Okay. And what is my H of S? 1 plus SP. Now, when I write this closed loop transfer function, I'll write that as, let's assume I'm writing that as CLTF, or only with transfer function. That will be equal to GS divided by 1 plus GS into HS. So till now we were having unity feedback. So when it is unity feedback, HS was equal to 1. Now here HS is not equal to 1, it is 1 plus SP. Correct? Now let's put in the values. So I will write K divided by S into S plus 2 whole divided by 1 plus K into S plus 2 into 1 plus SP. If we simplify it a bit, this S into S plus 2 and S into S plus 2 will go. Your CLTF, it will look like this: K divided by S square plus 2 plus Kp into S plus K. Correct? This is my closed loop. Now see, my omega n is given. My omega n is given as 5. Right? So my omega n is given as 5, and this omega n, and what is the value of k? If we compare, k is omega n square. On comparing with standard form, with standard form, for your easiness, I'll just write that here. Just remember it. I just told you, just remember it. It will come very handy. So this is my standard transfer function. So based on this, what is the value of k? K is omega n square. So that means my k is what? That means my k is 25. Okay. So the value of k is 25. Now let's find the value of p. So my 2 zeta omega n is equal to 2 plus kp. You see here. Now I know my 2 into zeta is given as 0.7 and omega n is given as 5. 2 plus 25 into p. Perfect. So if you solve it, we will get 5, 10. We'll get p as, solve it and tell me, we'll get p as 0.2. So very simple. Very simple question. What you had to do, you just had to write the system in, write the system closed loop transfer function, and after that, just compare, and you're done. Anybody has any question till now? Because now we will gradually increase the difficulty level. If you have any question, just tell me at this point.
Sir, I'm not getting value of peace.
Okay. See, until here, it is straightforward. You got the transfer function. Now you compare it with standard transfer function. Then this 2 plus kp, it will be equal to 2 zeta omega n. That's what I wrote here. 2 zeta omega n is equal to 2 plus k into p. This is K into P. K is different, P is different. I know the value of zeta n, I put in 0.7. I know the value of omega n, I put in 5. I know the value of 2 is 2 as it is. I have also calculated K as 25. P is unknown. So just multiply. Just
Sir,
multiply.
I got it, sir.
Uh-huh.
I got it, sir.
Okay, good. No problem. Thank you for asking. It's good that you ask questions. So that keeps us in the lecture. So now, very important, very important lecture. If you're able to solve it, you have understood. Or if you are able to generate idea that how we can solve this, then you have understood time response analysis, second order systems. You're given RS as this is your input. You have negative feedback. This is your OLTF, S into T into S plus 1. Similar to what we did right now, similar question. This is your CS, but now here it's unity feedback. So you are given a system. So when the system shown in figure 1, this is my figure 1, let's assume this is my figure 1. When this is subjected to unit step input, its output is given as this. The output looks like this. This is time. This is C of t. Just make it like this so that it's visible. Right? The response is like this. So obviously, which type of system it is? As of now, you should be able to comment that this system is underdamped system. Now it's also given, this is also given that this peak time is given. Peak time is 3 seconds. And this peak value is given as 0.254, 25.4%. And final steady state value is also given as 1. So for the system shown in figure 1 and this, wait. This is my figure 1. This is my figure 2. The system shown in figure 1, when we give unit step, when we give RS as 1 by S, the response looks something which is given in figure 2. Now, what is being asked? Determine the value of K and T from the response curve. Now, we have to find the value of K and we have to find the value of T. So now see, from the curve, what is given? Peak time is given. I'll just write solution. From the curve, what is given? Peak time is given. TP is given as 3 seconds. And peak overshoot is given as 0.254. Very good. So now do one thing. You see, if you see your system on the right, you see you are giving a negative feedback. You're also giving unit step input, and also your system is second order. If you just evaluate it, you will see it's a second order system. So you know, for a second order system, when you give step input, you already know the formula for peak overshoot. So what is the formula for peak overshoot? Peak overshoot is e raised to the power minus zeta into pi divided by 1 minus zeta square is equal to 0.254. Right? Now see how we will solve this. Very important, because in GATE, you do not have this calculator. You have that calculator, which is the inbuilt one. So still, if you do not have calculator, you have a simple calculator, still see how you should be able to solve it. Take logarithm both sides. So what you will get minus zeta pi divided by 1 minus zeta square is equal to natural log of this. If you take, you will, I don't know what's the value, but you will get something minus something value. That minus and this minus will go, right? That minus and this minus will go when you, okay, wait. Natural log of 0.254. right? You will take the logarithmic value. Let me calculate this value. Or if you have calculated, just tell me. 0.254.
Minus
Yeah,
1.37.
very good. It's minus 1.37. So my minus zeta pi divided by 1 minus zeta square is equal to minus 1.37. So main idea was this minus and this minus goes. Now the next step is you have from this expression, you will find the value of gamma, right? So now what you will do, my gamma into pi is equal to 1.37 into under root of 1 minus gamma square. Perfect. Take square from both the sides. What you will get? You will get zeta square. Sorry, I was reading it gamma. Pi square is equal to 1.37 into 1 minus zeta square. Perfect. Now what you need to find zeta square. I'll just do one thing. I'm doing this calculation in detail because this is a bit tricky sometimes. Students they do mistakes here. So now what I'll do, um, now what I will do, I'll just simplify this. Mm, Now, yeah, you'll just simplify this. So take this zeta here, then pi, take zeta square common. So it will be pi square plus 1.37, which is equal to 1.37. Then if you finally solve this whole, you'll find zeta is equal to 0.399, which is almost equal to 0.4. Okay, so your zeta will be equal to 0.4. So when you have got the value of zeta, when you have got the Suraj is, I don't know, there might be some calculation mistake or what, but yeah, you should get the value of zeta as uh, 0.4. Then when you have got the value of zeta, you also know what is my peak time. Your peak time is given as 3 seconds. 3 seconds. Pi by omega d is your like peak time. So you know omega d is also, you can write that in terms of omega n. So omega n into 1 minus zeta square. Then you can see your 3 is equal to, just put in the value of gamma, just put in the value of gamma, what you will get omega n, you will get equal to 1.14. So basically what you did as of now, you just found out the value of omega n and zeta, but that is not the question. What was the question? The question was to find the value of k and t. Now you see here, let's write the closed loop transfer function. So here HS is 1. So my closed loop transfer function, which is CS over RS, this will be given as, I'm directly writing, it will be T into S square plus S plus K. Now tell me, is it in the standard form? Can we compare it here with this? Wait. We cannot compare because here this T is in multiplication. So we have to simplify it a bit, right? So we can write it like this. If we simplify it, we can write it like this. Just multiply with t throughout. So we can write it as or take t common. When you take t common, I'll write this t here, the one which I took common from the numerator. It will be s over 1 by ts over k by t. Is it fine? Anybody has any doubt in this? Then you know my omega n square. My omega n square will be equal to k by t. And what will be my omega n? Under root of k by t, right? But you already know the value of omega n, or why we are doing it like this, just put in the value of omega n, right? Or let it be. For the time being, let it be. There is another expression which is 2 zeta omega n, which is equal to here 1 over t. You know zeta, you know omega n, you will get the value of t. So you will get the value of t as 1 by 2 into 0.4 into 1.14, which is equal to 1.096. When you get the value of t, you can easily find the value of k. My k will be t into omega n square. My k will be equal to 1.4165. I hope you have got the basic idea, at least how we have to solve such questions. Just a recap, I'll just recap. So you're given a control system where it's being said in the question that the response of this control system is given in this figure. Now, from the figure, you have to identify what is given. So in the figure you found, okay, my peak time is given, and at the same time, my overshoot is given. So when this is given, from this, you found out the values of zeta and omega n, because that's all you need. So from when you got the value of zeta and omega n, then you just compared, took the closed loop transfer function, just compared the response, and you got the results. You got the values. Anybody has any doubt here? If anybody has any doubt, just let me know. And this question, I want you all. I will not solve this. I want you all to solve this question. It's very easy. A unity feedback system has a forward path. You know G of S, that is the OLTF is given, which is K into S plus 8. So this is your G of S, it's OLTF. This K is the gain of the system. You have to find the value of K, find K for making the system critically damped. It's very easy. Everybody do it. I'll give you options as well. Option A is 4. Option B is 8. Option C is 16. Option D is 32. So you're given an open loop transfer function. You have to find the value of K for making this system critically damped. So I'll just give you a hint. So you know a second order system is critically damped when the value of zeta is 1, right? When the value of zeta is 1. But how we will find the value of zeta? Your value of zeta comes from CLTF. So first you will find CLTF, and it's given its unity feedback. I'll just write unity feedback. Unity, obviously, unity negative feedback. So it's unity feedback. So it's given its unity feedback system, and open loop transfer function is given. First, what you do, find Shamita has solved it. Very good. Yeah, 16 is the correct answer. You've solved it very quickly. That's a good news. So find CLTF. Shamita, can you please explain? Oh, many people are coming up with answers. Anybody who is willing to explain this to others who have not solved it, find CLTF initially and then just compare. Put zeta equal to 1. You'll get the value of K. Anybody, Ishwar Singh, Pawar, can you explain this to others?
Yeah, yes, I can.
Yeah,
So
please.
we have given
The CLT.
open loop. Yeah, you can explain, Shamita.
Yes,
CLTF
Shamita,
is
please.
first we have
Hmm.
first we have to find the CLTF, and we'll get the denominator as s square plus 8s plus k. So the coefficient of s is 8. So we will equate it to the standard deviation. So we will get equal to 2s omega n. Here omega 2 2 eta omega n. Here eta is 1. So we'll get to omega n as 4. The k value is omega n square. So 4 square is 16.
Brilliant. Excellent. Very good. So I hope others are able to understand. So you will get similar type of questions in your gate, right? In your gate exam and as well as in your this NPTEL final exam. I don't know whether there are any such questions in the assignment, but if you're able to solve these questions, you don't need to learn second order systems again. But if you're not, then please go and learn second order systems again. Now we'll do one last question from second order systems, and after that we'll see some controller questions. And I want, it's a bit tricky, but we have solved a question based on this. So I want all of you to solve it. So keep your calculators ready. Uh, so you're given the response of a second order system. You're given the response of a second order system where the steady state value is 1. The response looks something like this. Fine. The response looks something like this. This peak value is given as 1.25. This peak time is given as 0.01. 0.01. Actually, this peak time is not given. Sorry, peak time is not given. Scale is given. The scale is 1.25. It's 1. And so on. Scale is given, but peak time is not given. So you yourself have to first find, sorry, peak value you have to yourself judge. So you are given again, we have just solved few minutes before we solved similar question. So here,
What
I'll
is
just give you
case?
a hint. Yes, 0.01 seconds is your peak time. And what is your MP? Can anybody tell me what is your MP?
1.25.
No. It's not 1.25. 1.25 is scale. See, your system had to settle on 1, but it's settling, it's initially going above 1. It's going to 1.25. It means it's going 25% beyond 1, right? So if it is going 25% beyond, then your MP, it should be 25%, or it will be 0.25. Did you get it? Did you get it? What I wanted
What
to,
is
what I want to
case?
convey. Uh-huh.
Yes.
What is case? 1.2. What is case?
No, I didn't ask you what you have to do. So as of now, you are given a peak time and overshoot. This is given. And what the question is saying, the unit step response of a linear control system is shown in the figure. Fine. Find the transfer function. So find the CLTF. So you need to find this transfer function actually, omega n square s square plus 2 zeta omega ns plus omega n square. Basically, you need to find zeta and omega n. Because when you have zeta and omega n, you have the transfer function. Again, we have solved a similar type of question. The only trick here was to identify MP. MP is 0.25 here, not 1.25. If you take 1.25, then you are bound to make mistakes. Okay? Have you understood this? No need to solve this because you have solved. Shamita is asking what is scale. A scale means the value. The value. See, this is response C of t. Scale means this y-axis. It's 1 here, then it will be 1.20 here, then 1.25 here, 0.5. This is what I meant by scale. 0, 0.01, so on and so on and so forth. Clear, Shamita? I'll just write answer for your, you will solve it. Everybody, you should solve it. The answer will be, I'll just write the answer, 342.77 square. So omega n will be 342.77 s square plus 274.2 into s plus 342.77 square. This is the answer. You just try yourself. We're not going to solve it because we are running short of time. We have to cover controllers as well. Anybody has any doubt until here? Then we can move to controllers part. Okay, means nobody has any doubt. Let's start controllers. I know many of you joined late. I explained things in the beginning, but let me again explain. I told you in the beginning that whenever we are studying a second order system in particular, or any system, but here we are dealing with second order systems, so I'll talk about second order systems only. Whenever we are being given a second order system, so you study these rise time, peak time, settling time, etc., etc. But what is the advantage? I told you if a system has less rise time, that means that system is faster. If a system has less rise time, that means the system is sluggish. Again, if the system has peak overshoot, that is not desired. It's never desired. For example, you have a fan which is operating, which is the higher operating limit of that fan is 200 volts, let's assume. 200 RPM, let's assume. So when you are giving its input voltage and it if it exceeds that, so it will that is a problem for you. So you only want your system to be at 200 RPM. In this case, fan. You don't want your fan to rotate more than 200 RPMs, right? Why? Because that is not desired. If that happens, my fan will burn or it will crash, right? So it depends. What are you desiring for? Do you want less overshoot, or do you don't want overshoot? Or you will say, okay, this much of overshoot is okay, but I don't want more overshoot. Or somebody says this much of rise time, my rise time is 5 seconds, that is okay, but I don't want, because I don't want faster response. That's okay if my response is a bit slower, but I want more accuracy. I don't want more overshoot. Now, how to find, how to control, how to get desired rise time, how to get desired overshoot, how to get desired settling time, then these controllers come into picture. So controllers help us get that desired rise time or desired performance specifications. These controllers help us. When we will see frequency response analysis, then we will see some other parameters, bandwidth, resonant peak, or other bandwidth, right? Other parameters. So we will have again compensators, then we will design compensators. So when you have questions from these controllers or from compensators, you basically have questions like this. You're given a system with rise time this, peak time this, and this is its overshoot. Design a controller so that rise time is decreased, or this overshoot is decreased, rise time is increased, something similar to this. Perfect. So basically, I told you in lecture 2 or lecture 3, this controller is always connected before the plant. I'll just make that diagram again. So that you are able to understand things in a better way. If this is your plant, so this is your output, C of t. Let's assume this is your output, or I'll just write output. Let's not confuse you because I'm writing detail in detailed way. And this is some input to the plant, right? And here I will have controller. I will write controller here. Controller. Here I will have the summer block here I will have some feedback, right? Any feedback signal h of s, or I'll just write feedback. And this is my input. Reference signal, actually, this is not input. This is reference signal. Why I said reference signal? Because this is what we want to track, or this is what we want to control. Perfect. So from this, we will have error. The output of this is called actuating signal. I'll just say it again. See, this is a basic block diagram of a closed loop control system. You have a plant. The output is fed back to the input. We compare the input signal, the reference signal, with the error, with the feedback, and we get error. That error drives the controller, and controller gives some output. This controller output, this is called actuating signal. Remember, is from now onwards, this controller output, it's an actuating signal. Why it is called actuating signal? Because controller output is going to act as input to the plant, right? So this, before this controller, there is another block which is called actuator that actually makes that controller output compatible to the plant, so that it is actually compatible to the plant, right? For example, if it is a DC motor, so then the input has to be some voltage, right? If there is some mechanical system, so there has to be some rotating, this actuating signal, it has to do something, a rotating part, motor or something like that, right? So the output of the controller is called actuating signal, and the input to the controller is error, right? Now I am telling you, this controller helps us to achieve the desired goals. For example, I want desired rise time, peak time, etc., etc. It is the controller that is helping me. If the output of the signal is actuating signal, if the output of the controller, which is the actuating signal, if this actuating signal is proportional to the error signal, see, input is error, output is actuating signal. If this actuating signal, let's assume my actuating signal is P of S. If this actuating signal P of S, if it is directly proportional to my error P of S, then I can also write it like this, some proportionality constant. Perfect. So if my actuating signal is directly proportional to the error, then the controller is called proportional controller. Then the controller is called proportional controller. If my actuating signal is directly proportional to the integral of error, then my controller is called integral controller. If my actuating signal is directly proportional to the derivative of error, then my controller is called derivative controller. If my actuating signal is proportional to the combination of integrating and then we can actually combine the effects. We can have proportional and integral controller together. We can have proportional and derivative controller together. We can have proportional and integral and derivative controller together. It depends on what we want to desire, what we want to achieve, what we are desiring for, right? So you must have, the professor must have taught you. So if you have not seen the lectures, not seen the notes, please do. So the professor must have explained in detail what is the function of proportional controller, when we want our steady state error to be zero or close to zero, should we use proportional controller or integral controller or a combination of proportional integral controller, etc., etc. There are pros and cons of all of these controllers. So basically, the basic idea is the game between actuating signal and error signal. The game is between the actuating signal and the error signal. So you just have to remember like that. So that's a different story, what a proportional controller does, what an integral controller does. But what we will see here, we will see some mathematical stuff, what happens when you add, or what are the expressions of a proportional controller. For example, I told you, so a proportional controller, this only has one constant, Kp. If it is an integral controller, it has Ki, but since it's integral, if you remember Laplace, it will be Ki over S. If it is derivative, it will be S into Kd, right? So this is my P, this is my I, this is my D. Now, if it is combination of proportional and integral, my controller effect will be something like this, Kp into Ki by S. If it is a combination of, this is my Pi controller. If it is a combination of proportional and derivative, it will be something like this. It will be PD controller. Why do we use it? That's a different story. You have to yourself look. So when I want my rise time to be less, my transients to die off early, my damping to be less, which controller I have to use? The professor must have explained in detail. So if you want to use PID, which is a very well-known used controller in industry, you have an expression of the controller like this. Kp plus Ki by S and S plus Kd, right? So this is the expression for a proportional derivative, integral and derivative control. If you remember this, you should be able to write the expression for proportional, proportional integral, proportional derivative, proportional integral derivative, right? So if I'm saying in the question that you are using a proportional integral controller, then the transfer function of that block, that controller block, which comes in, which comes before the plant, that will be given by this. If I say I have a PI controller, then the transfer function will only be this part, right? If I say I have only P controller, then the transfer function will only be Kp. There is no S, it's only proportional. Perfect. So I hope you have understood you've got the idea. If that is the case, now let's see one simple question. Let's start our discussion with one simple question. A first order system has a transfer function, just for understanding purpose, or I'm giving a first order system initially. So it's an open loop transfer function which is given. So it's a first order system. Why? Because there is only one S initially when it's OLTF. With a PI controller, the closed loop system in unity feedback. So then what we did, we actually took unity feedback, right? And the closed loop system has the characteristic equation. Characteristic equation is like this. See, when I write the closed loop transfer function, I write 1 plus GS into GS into HS. If my HS is 1, or if that is not the case, whatever is in the denominator, if you put that equal to 0, you get the characteristic equation. So whatever is the denominator, just equate that to 0. That's your closed loop transfer. That's your that's your characteristic equation. So in the question, it is given that you are given a first order system with this transfer function. When a PI controller, with a PI controller with a PI controller, just try to understand the question, and it's basically the same thing we have been doing. With a PI controller, the closed loop system with a unity feedback has the characteristic polynomial, what is that? P of S. It's given as S square plus 3S plus 4. So this is given as the characteristic polynomial when we add a PI controller. And what is being asked? Find Kp and Ki. Now see how to solve such questions. Given a first order system, so this is my plant. Plant is this, 1 divided by S plus 2. Now the question is saying with a PI controller. Now I have to add a PI controller that will be somewhere, that will be here. PI controller always comes before the block. So PI controller is a P and I. So my transfer function will be KP plus KI by S. I told you in just minutes before. This is my PI controller. And here, then it is saying unity feedback. This is my output. Unity feedback means I'm doing nothing, just adding it to minus. This is my input signal, RFS. Perfect. So then what happens? The closed loop polynomial has a characteristic polynomial of this thing. Now let's try to solve this. Find the transfer function, closed loop transfer function. So let's name this as g of c, and let's name this as g of s because this is plant. I told you when the blocks are in cascade, their transfer functions get multiplied. We have learned this. So what will be the net transfer function, right? So or let's not write the net transfer function. We will just write like this: GC is KP plus KI by S. Then my net transfer function CLTF will be equal to GC into G divided by 1 plus GC into G into, there is no H. H is 1. So this is my closed loop transfer function. Just put in the values. It will be KP plus KI by S into 1 plus S, 1 divided by S plus 2 divided by 1 plus KP plus KI by S into 1 divided by S plus 2. If you simplify it, just go step by step and simplify it. What you will get? You'll get something like this: SKP plus KI divided by S square plus KP plus 2 into S plus KI. Also, it was given that the characteristic polynomial of this closed loop system is S square plus 3S plus 4. Now you compare your characteristic polynomial. This is your characteristic polynomial. You see, on comparing KP plus 2 is equal to 3, it implies your KP is 1. Perfect. Similarly, your KI is already given as 4. It's coming like that. See, KI is this. Perfect. So we got the values of KP and KI. Somebody has asked something. KP 1, KP 4. Oh, good. Very good. Very good, Ishwar Singh. So anybody has any doubt, please ask. The next question you will do yourself. Very good question. It's a gate level question, or even more tougher than gate, because in gate, PID controllers, they don't ask difficult questions. But yes, if somebody is preparing for ES, engineering service examination, they might expect this question in the ES exam. So what's given? Consider a system with transfer function. So we are given a transfer function, an open loop transfer function, S plus 1 whole square. Perfect. Now an integral controller. So my controller this time, GC of S is KI over S, because it's saying an integral controller gives a closed loop pole at S equal to minus A. Now this integral controller gives a closed loop pole at S equal to minus A. Find the value of KI. So if nothing is working out, if nothing is clicking you when you are solving questions for second order system, just find the CLTF. Because when you find the CLTF, you'll see things are becoming visible. See. Yeah, see. What is my CLTF? CS over RS, or CLTF directly I'll write. That will be GC, controller transfer function, into G, because I told you integral controller. See, the question has written they are using an integral controller. So if they are using a controller, obviously there has to be feedback. If it is not mentioned which feedback is there, obviously then it is unity feedback. It is not mentioned is positive or negative, it's negative feedback. So whenever there is controller, and it's also saying gives a closed loop pole, so it means obviously there's a feedback, right? So this will be my CLTF, GC into G plus 1 plus GC into G. Perfect. Now let's put in the values. My integral controller, only integral controller is being used. So it will be Ki over S into 1 divided by S plus 1 whole square, whole divided by 1 plus Ki by S into 1 divided by S plus 1 whole square. Just solve it a bit. What we will get, Ki by S into S plus 1 square plus Ki. So you get something like this. Now let's go to question. So you have done this much. Now let's go to question. Now question is saying the closed loop gives a pole at S equal to minus A. Now this is my closed loop transfer function. It means it has two poles because it has actually three poles. Right, it has actually three poles because see, S plus 1 whole square, the two S square term is here, and there is also one S before S plus 1 whole square. So it means there are actually three poles. But the question is saying the value of the question is saying it gives a closed loop pole at S equal to minus A. At S equal to minus A, it gives a closed loop pole. That means this will satisfy this equation at S equal to minus A. This equation will be satisfied. Just put the value of A S as minus A. Then what you will get in the denominator, minus A into minus A plus 1 whole square plus Ki equal to 0. We have to find the value of Ki. Then what will be the value of Ki? Ki will be equal to A into 1 minus A whole square, right? A into 1 minus, or if we solve it, it will be, just evaluate A 1 minus A whole square. So it will be A cube minus 2A square plus A, or this, either this is the answer or this is the answer. It depends on the options, right? So then the value of Ki is this. Perfect. Now there is one more question, one last question, or maybe we'll do one more question after that. Now we got the value of Ki. We got the value of Ki as this. Question is, determine the value of A that maximizes the integral gain. Or in other words, it is saying find the value of A such that the value of Ki is maximum. So this is, see, this question, but you will then think, oh, from which part they're asking this question. This is basic mathematics, right? So they are saying, when will the value of K be maximum? At what values of A? So what you will do, you will differentiate dk over dA. So what will be dk over dA? 3a square minus 4a plus 1. Now, just put this value as 0, then dk I by dA, this should be equal to 0, implies I will get some values where we will check the second derivative. and where the point where the value of a, where my second derivative is minimum, that will give me the maximum. That value will maximize the value of k. So when we solve, we get a is equal to 1 or a is equal to 1 by 3. Now see, second derivative, dki over dA square, that will be equal to 6a minus 4. Now d square ki by dA square at a equal to 1, what will be it? 6 minus 4 equal to minus it's equal to 2, and d square of ki dA square at a equal to 1 by 3, 6 into 1 by 3 minus 4 minus 2. So it means the value of double derivative is minimum at a equal to 1 by 3. It implies a equal to 1 by 3 maximizes the integral gain. Or in other words, when a is 1 by 3, the value of ki is maximum. So maxima and minima, it comes from your class 12, right? So this was some basic touch of PID controllers. Now let's do one last question, which should also clear all your doubts. So yeah, because this part is also based on similar theory that we have covered. So the question is, derivative feedback is employed. So derivative feedback means derivative controller is used in feedback, right? So derivative feedback is okay. I'll write the whole question. Derivative feedback. This is the last question for the day. Derivative feedback is employed in the control system. In the control system shown in the figure. And why we use derivative to improve its damping? So it means, why do we use derivative controllers? We use derivative controllers to improve damping. Similarly, we use PI controllers or integral controllers to improve steady state performance, because in case of proportional integrals in controllers, there is always a steady state error. So just go through the lecture and maybe you'll see the pros and cons of all the controllers. So we have, as of now, it's given in a control system, we are employing a derivative feedback to improve damping. If the required, I told you why we are using these controllers, we want something desired. If the required damping factor of the system is if the required damping ratio of the system is 0.5, the value of KD must be adjusted to option A 4, option B 19, option C 0.25, option D 6. Now see the diagram. And try to understand the question. See, I'll just explain this question. It's written in the question, derivative feedback is employed in a control system shown in figure. You can see here, we have used a derivative feedback. Why we have used derivative feedback? We want to improve the damping, right? So we want to improve the damping. Damping means we want to improve this. We want to play with this value. And what do we want? So this can be anything, 0.1, 2, 3, 4, anything. So, but we want this zeta to be 0.5. So I told you we use controllers to get the desired values. So if we want this zeta to be zeta to be 0.5, it means we have to play with the value of KD. So we have to adjust this KD in such a way so that my zeta becomes 0.5. So that my zeta becomes 0.5. This is the question. So what should be the value of KD so that the value of zeta is 0.5? Perfect. Now see, as of now, if you are not able to, if nothing clicks your mind, what did I say? Just try to solve the circuit. Reduce this loop first, and then reduce this whole loop, get the closed loop transfer function. That's it. When you get the closed loop transfer function, things will be visible. Things will be visible. Perfect. So see, this whole part, I'm denoting it with GD. Okay. So what will be my GD? My GD, it's negative feedback. So my GD will be 1 divided by S into 4S plus 1 divided by 1 plus 1 divided by S into 4S plus 1 into S into KD, right? Same thing, GS divided by 1 plus GS, HS. Perfect. So when you solve it, you will get GD to be equal to 1 divided by 4S square plus S into 1 plus KD. Perfect. I'll write capital D. Perfect. You got GD. Now see, I will make the net circuit. What is left? What is left in the circuit? This 100 is there. Then here only this GD is there. So I'll write GD. Then you have output C of S, and then you have in this feedback, negative feedback. Now solve this circuit. Write the net transfer function G of S. That will be GD into 100 divided by 1 plus GD into 100, right? 1 plus GD into 100. Just put in the values because HS is 1. Just put in the values. If you put in the values, what you will get? You will get your GD equal to 100 divided by 4S square plus S into 1 plus KD plus 100. Now let's compare. Is it in a standard form? No. As of now, it is not in a standard control form. This is G of S. It's not in the standard control form. Why? Because here we have this term 4. Let's take 4 common, and when the common one will go here. So the net transfer function will be 100 divided by 4 is 25. Then we have S square plus 1 plus KD divided by 4 into S plus 25. Now it's in standard form. So when it is in standard form, what is the value of omega n? What is the value of omega n? Omega n square is 25. It implies my omega n is 5 radians per second. And also my zeta is 0.5. Also my zeta is 0.5. Then 1 plus kd by 4 is equal to 2 zeta omega n. It implies 1 plus kd over 4 is equal to 2 into 0.5 into 5. Perfect. So my kd is equal to 4 into 0.5 into 5 into 2 minus 1. It implies my kd is equal to 4 to the 8, it was a 40, 40 by 0.5 is 20. This whole part will be 20 minus 1, 19. So my kd was 19. Did you understand? Did you understand like how I solved this? So with these questions in mind, I think you should be easily able to solve uh, assignment questions. If you have any doubt in any assignment question, we can discuss any question. We have covered these controllers a bit. We have also covered second order systems. We have done some good questions. In your assignment questions, you only have uh, find rise time, peak time, settling time, and overshoot. Find whether a system is critically overdamped, underdamped, or undamped. And also, I think some questions are related to stability. So when a system is stable or critically stable or whatever. So that means, so if it is a second order system, I'll just make it clear. Second order system, 2 zeta omega ns and omega n squared. Then the coefficients of this second order system, they should be of the same sign, right? They should not be non-zero and they should be of the same sign. If that is the case, then the system is stable. We will learn this in the next week, the upcoming week, and then we will learn Raut-Howitz criteria, right? So this will be more like this. We will understand more in Raut's way. But as of now, just remember, if you are being given a second order system, you're asked when the system will be stable. The condition is all the coefficients should be greater than zero, should be of the same sign. They can be either positive or negative, right? They should be of the same sign and they should be present. But we cannot generalize that. Because of obviously for third or other order systems, as of now, we cannot do that unless and until we learn Raut-Howitz criteria. But yes, with the questions that we have discussed in this week, I think you should be able to solve all your assignment questions. So anybody has any doubt? Okay, so if you do not have any doubt, then I'm just stopping the recording. Thank you very much for attending this session. I don't know why the attendance was low today, but anyway, those who joined, I hope you have been benefited. Thank you very much.
Thank you, sir.